Next, relationship between electrical energy and chemical energy. The electrical energy produced in a cell is defined as the product of the quantity of electricity that passes through the cell and the EMF of the cell. Example, electrical energy is equal to quantity of electricity into EMF. For every 1 mole of electrons transferred in the cell reaction, example, for every 1 gram equivalent of the ions deposited, the quantity of electricity that flows through the cell is 1 Faraday. Thus, if 1 mole of electrons are transferred in any cell reaction, the quantity of electricity passing through the cell Nf Faradays is if E is the EMF of the cell, then electrical energy is equal to NFE. Till the middle of the 19th century, it was generally accepted that the electrical energy produced in a reversible cell was equal to the chemical energy, measured as heat when the reaction takes place in a single beaker. This view was supported by the following results. In Daniel cell N is equal to 2, hence in order that 2 gram equivalents of copper may be deposited or 2 gram equivalents of zinc may dissolve, 2 Faraday of electricity must flow through the cell. Further, for it, this cell is equal to 1.10 volt. Hence, electrical energy produced is equal to 2 into 96500 into 1.1 joules is equal to 2.212300 joules. The heat produced when 2 gram equivalents of zinc rod react with the same copper sulfate solution in a single beaker is found to be nearly 212,000 joules. This is in good agreement with the electrical energy. However, later on it was observed that for a large number of reactions, the electrical energy produced was not equal to the chemical energy. Hence, it was suggested by Gibbs and Helmholtz that the electrical energy produced in a reversible cell is equal to the decrease in free energy accompanying the cell reaction. Thus, if del G represents the change in free energy, we must have minus del G is equal to NFE. Further, according to Gibbs-Helmholtz equation, we have del G is equal to del H plus T of curly G del G upon curly T at constant pressure. Substituting the value of del G from equation 1 and equation 2, we get minus NFE is equal to del H plus T into curly of minus NFE upon curly T at constant P. NFE is equal to minus del H plus T NF into curly E upon curly T at constant P, which is equation number 3. Or E is equal to minus del H upon NF plus T into curly E upon curly T at constant P. From equation 3, it is evident that whether electrical energy produced is equal to less than or greater than the enthalpy change depends upon the sign of curly E upon curly T. Example, the temperature coefficient of the EMF. Thus, if curly E upon curly T is extremely small, almost equal to 0 as in the case of Daniell cell, the electrical energy produced is equal to the enthalpy change. Second, if curly E upon curly T is positive, the electrical energy produced is greater than the heat of reaction at constant pressure, the additional energy being absorbed from the surrounding. Third, if curly T E upon curly T is negative, the electrical energy produced is less than the heat of reaction at constant pressure, the difference of energy being lost as heat to the surrounding. Calculation of thermodynamic quantities of cell reaction del G, del H and del S. As already explained above, del G is related to EMF according to the expression del G is equal to minus NFE, which is equation number 5. Thus, knowing the EMF del G can be calculated. Equation 3 or 4 may be written as del H is equal to NF of T into curly E upon curly T at constant P minus E, which is equation number 6. Thus, knowing the EMF E and the temperature coefficient of the EMF curly E upon curly T at constant P, the heat of reaction del H can be calculated. Having known the values of del G and del H, the entropy change del S accompanying the reaction can be calculated using the relationship del G is equal to del H minus T del S, or a direct relationship from del S in terms of EMF can be obtained as follows. From equation 2, del G minus del H is equal to T of curly of del G upon curly T at constant P is equal to T of curly of minus NFE upon curly T at constant P is equal to minus NFT of curly E upon curly T at constant P, which is equation number 8. From equation 7, del G minus del H is equal to minus T del S, which is equation number 9. Comparing equation 8 and 9, we get minus T del S is equal to minus NFT of curly E upon curly T at constant P, or del S is equal to NF of curly E upon curly T at constant P, which is equation number 10. Thus, the entropy change del S can be calculated directly from the knowledge of the temperature coefficient of the EMF. Standard hydrogen electrode and measurement of electrode potential. The terms electrode potential and standard electrode potential have already been defined in section 6.9. The absolute value of the potential of a single electrode cannot be determined. It can only be measured by using some electrode as the reference electrode. The reference electrode used in the standard hydrogen electrode, in which hydrogen gas at 1 atmospheric pressure is bubbled around a platinum foil dipped into acidic solution having concentration 1 molar. The electrode potential of the standard hydrogen electrode is taken as 0. To determine the electrode potential of any electrode, a cell is set up using this electrode as one of the electrode, and the second electrode is the standard hydrogen electrode. The EMF of the cell is measured, as the EMF of the cell is the sum of the oxidation potential of the electrode where oxidation takes place and the reduction potential of the electrode where reduction takes place, and one of the electrodes involved is the standard hydrogen electrode, for which the electrode potential is taken as 0. The EMF of the cell will directly gives the electrode potential of the electrode under investigation. The direction of the flow of current further indicates whether oxidation takes place or reduction takes place on the electrode under investigation with respect to the hydrogen electrode. Accordingly, the electrode potential is termed as oxidation potential or reduction potential. The determination of the electrode potential may be further illustrated with the help of the following two simple examples. First, determination of standard electrode potential of zinc in solution of zinc ions electron. A cell comprising of zinc electrode immersed in 1 mole of zinc sulfate solution and a standard hydrogen electrode is set up as follows. EMF of the alpha cell comes out to be 0.76 volt. Hence, standard electrode potential of zinc in zinc ions electrode is equal to 0.76 volt. Further, the direction of flow of current indicates that oxidation takes place at the zinc electrode. Hence, 0.76 volt is the standard oxidation potential of the zinc electrode. Second, determination of standard electrode potential of copper in copper ions electrode. A cell comprising of copper electrode immersed in 1 mole copper sulfate solution and a standard hydrogen electrode is set up as follows. EMF of the cells come out to be 0.34 volt. Hence, standard electrode potential of copper in copper ions electrode is equal to 0.34 volt. Further, the direction of flow of current indicates that the reduction takes place at the copper electrode. Hence, 0.34 volt is the standard reduction potential of copper in copper ions electrode. It is important to mention here that it is common practice to express all the electrode potential as reduction potential. Since the reduction half reaction is just the reverse of the oxidation half reaction, therefore reduction potential is obtained from the oxidation potential by simple changing the sign. Example for an electrode, reduction potential is equal to negative of oxidation potential. Other reference electrode and measurement of electrode potential. The use of hydrogen electrode as the reference electrode is not convenient, obviously, because it involves the use of hydrogen gas. Hence, a number of other electrodes have been used as reference electrode. The most common out of these is the calomel electrode, the construction of which has already been described in figure 6.11 and 6.12. The electrode potential of the calomel electrode at 25 degrees Celsius using 0.1 normal KCl 1.0 normal KCl and saturated KCl solution have been determined accurately. These are given below as a reduction potential. Concentration of KCl solution is 0.1 normal, then its reduction potential is positive of 0.3338 volt. When concentration of KCl solution is 1.0 normal, then its reduction potential is positive of 0.2800 volt. When it is saturated solution, then its reduction potential is 0.2415 volt. To determine the electrode potential of an electrode cell using this as one of the electrode and the calomel electrode as the second electrode is set up, the EMF of the cell is measured and then the following expression is used to calculate the required electrode potential. EMF of the cell is equal to oxidation potential of the electrode where oxidation takes place plus reduction potential of the electrode where reduction takes place. The calomel electrode using 0.1 normal KCl solution is usually preferred because it has lowest temperature coefficient. However, the calomel electrode using saturated KCl solution is convenient for many purposes and is often used. The method for determination of electrode potential using calomel electrode as the reference electrode may be illustrated with the help of the following examples. First, determination of the standard electrode potential of zinc and zinc ions electrode. A cell composing of zinc electrode immersed in 1 molar zinc sulfide solution and the calomel electrode, say using 1 normal KCl solution, is set up as follows. EMF of the above cell at 25 degrees Celsius comes out to be 1.083 volt. Further, the direction of flow of current shows that oxidation takes place at the zinc electrode. Hence, we have EMF of the cell oxidation potential of the zinc electrode plus reduction potential of the calomel electrode. Example 1.083 is equal to oxidation potential of the zinc electrode plus 0.280. Therefore, oxidation potential of zinc electrode is equal to 0.803 volt. Second, determination of the standard electrode potential of copper in copper ions electrode. A cell comprising of copper electrode immersed in 1 molar copper sulfate solution and the calomel electrode, say using 1 normal KCl solution, is set up as shown. EMF of the upper cells come out to be 0.018 volt. Further, the direction of flow current shows that reduction takes place at the copper electrode. Hence, we have EMF of cell is equal to oxidation potential of calomel electrode plus reduction potential of the copper electrode. Example 0.018 is equal to minus 0.280 plus reduction potential of the copper electrode. Therefore, reduction potential of the copper electrode is equal to 0.298 volt. Similarly, Ag and AgCl electrode has also been used as a reference electrode. A standard electrode potential has been found to be 0.02224 volt at 25 degrees Celsius. Electrochemical series. The standard electrode potential of a large number of electrodes have been determined using standard hydrogen electrode as the reference electrode, for which the electrode potential has been arbitrarily fixed as 0. As already mentioned, it is a practice to express the electrode potential as a reduction potential. Since reduction half reaction is just the reverse of oxidation half reaction, the reduction potential of any electrode is obtained from its oxidation potential by simply changing the sign. Further, according to the latest convention of sign, the electrode at which reaction takes place with respect to hydrogen electrode has a positive oxidation potential or expressed as the reduction potential. It will have a negative sign. The various electrodes have thus been arranged in order of the decreasing values of standard reduction potential as shown in table 6.2. This arrangement is called electrochemical series. Applications of the electrochemical series. First, to predict the relative ease of oxidation or reduction of various elements. As per convention, positive sign is used to represent the reduction potential. That implies that greater is the reduction potential, more easily is the substance reduced, or in other words, stronger oxidizing agent it is. Thus, in table 6.2, Sf2 has the highest reduction potential and lithium ion has the lowest reduction potential. This means that fluorine is the reduced most easily while lithium ions are reduced with greatest difficulty. In other words, fluorine is the strongest oxidizing agent, whereas lithium ions are the weakest oxidizing agent. Conversely, writing the reactions in the reverse order, it can be postulated that lithium will be oxidized most easily and hence is the best reducing agent, whereas fluoride ions are oxidized with greatest difficulty and hence are the weakest reducing agent. Second, to predict whether a metal reacts with acid to give hydrogen gas. In order that a metal may react with an acid to give hydrogen gas, the following reaction should take place. Metal plus hydrogen ion gives metal ion plus hydrogen gas, which can be split into two half reactions as metal gives metal ions plus electrode, which is oxidation half reaction, or hydrogen ion plus electron gives hydrogen gas, which is reduction half reaction. Example, the metal should have the tendency to lose electron. Example, undergo oxidation with respect to hydrogen. In other words, the metal would have a negative reduction potential. Thus, all metals lying below hydrogen in the electrochemical sequence react with the acid to give hydrogen gas. Further, evidently, lower the reduction potential, higher is the reductivity. Alternatively, as will be seen later, the EMF of the cell comprising of the oxidation half reaction and reduction half reaction as written above may be calculated by adding the oxidation half potential and the reduction half potential. If EMF comes out to be positive, the reaction takes place. Third, to calculate the standard EMF of a galvanic cell, as electrochemical cell is based on a redox reaction which can be split into two half reactions with first oxidation half reaction, second reduction half reaction. Standard EMF of the cell is equal to standard oxidation potential of the oxidation half reaction plus standard reduction potential of the reduction half reaction. Also, its oxidation potential is equal to negative of reduction potential. The above expression may also be written in the form as standard EMF of the cell is equal to standard reduction potential of the reduction half reaction minus standard reduction potential of the oxidation half reaction. Further, as in the representation of a cell, the electrode on which oxidation takes place is written on the left hand side and the electrode on which reduction takes place is written on the right hand side. The above expression may also be written as standard EMF of the cell is equal to standard reduction potential of the RHS electrode minus standard reduction potential of the LHS, or equal to E naught of cathode minus E naught of anode. For to predict the spontaneity of a redox reaction, a reaction is spontaneous if del G is negative. Example, there is decrease in free energy in the cell reaction, but the del G is related to the EMF of the cell. According to the reaction, del G is equal to minus NFE. Thus, del G is negative only if EMF E is positive. Hence, to see whether a given reaction is feasible or not, the EMF of the cell based upon the given redox reaction is calculated. If EMFs come out to be positive, the reaction takes place. If the EMF comes out to be negative, the direct reaction is given one cannot take place. The reverse reaction may take place. This is illustrated by the activity and activity coefficient of electrolyte. It is observed that when an electrolyte is dissolved in water, the effective concentration of the ions in the solution is different than the actual concentration. This is obviously because of the fact that in the presence of a large number of ions present in the solution, the freedom of movement of each ion is hindered. It is just like the fact that if only one swimmer is swimming in a pool, he has a greater freedom of movement than if a number of other swimmers are also swimming in the same pool. The effective concentration of an ion or the electrolyte in a solution is called its activity. The activity of an electrolyte in a solution is usually represented by A. It is related to the actual concentration expressed as molality M by the equation alpha is equal to gamma into M, where gamma is called the activity coefficient. Example, gamma is equal to alpha upon m. Hence, activity coefficient may be defined as the ratio of the activity to the actual concentration or molarity of the solution. For real solution, activity is not equal to molality. Hence, gamma is different from unity. For ideal solutions, alpha is equal to m and hence gamma is equal to 1. It is observed that as the concentration is increased, the activity coefficient first decreases below unity, passes through a minimum and then begins to increase and then may attain values much greater than 1. It may be mentioned that the activity of an electrolyte is in fact the product of the activities of its ions. For univalent electrolytes, A is equal to A positive and negative. Since the activity of the individual ions cannot be determined, a term called means ionic activity has been introduced. The means ionic activity for a univalent electrolyte is defined by the expression A positive negative is equal to under root A is equal to under root A positive and negative. Equation number 4. In a similar manner, the term mean activity coefficient Gamma positive negative has been introduced for univalent electrolyte as is defined by the expression gamma positive negative is equal to under root gamma positive gamma negative. Further putting alpha positive is equal to gamma positive m positive and alpha negative is equal to gamma negative m negative. Equation 4 becomes a positive negative is equal to under root a, which is further equal to gamma positive m positive into gamma negative m negative. For univalent electrolyte, M positive is equal to M negative is equal to M, and gamma positive is equal to gamma negative is equal to gamma M positive negative. Therefore, under root alpha is equal to under root M square gamma square positive negative, or alpha is equal to M square gamma square positive negative, which is equation number 6. The determination of activities and activity coefficient has been discussed later. That's it for today. Thank you.